This is Free Range Digital Design Foundation Modeling, Chapter 25, Lecture number 2. We've been working with finite state machines, and now we're moving towards using a finite state machine to design a sequence detector. Sequence detectors are a good starting point for state machine design. Their circuits are actually useful. They're fairly simple to generate the state diagram for the state machine. We're not going to be actually working with state machines. Once we have the state diagram, we can choose any number of ways to implement that state diagram in hardware. Now the issue is it's pretty much cookbook, however you want to do it. Once again, the engineering step is generating a state diagram. We have the overall view of a sequence detector. What it's doing is, this is your state machine that's going to be a sequence detector. This is an input bit, and it's looking for a special sequence on that input bit. And so it's a serial line. It's going to look at the bits according to each clock edge. Every clock edge, it's going to look at a bit. So if it finds that sequence, it's going to indicate it found the sequence by turning the Z on. So this is an example where we're looking for the sequence 101. What we're going to do here is we have two different ways to look at it. We can look at it as if it's non-resetting or resetting. So here we go, chunking through here. This is the input. These are the inputs per each clock cycle. And what we see here's the input, and then we see a 101, and that is what we're looking for. So both of these outputs in the setting and non-resetting case are going to say, hey, I found the 101. The difference between these is that in the non-resetting case, it can reuse previous bits as part of the sequence. So here's a 101 and it's indicated. There is a 101 and it's indicated again. So essentially it reused that one bit in there, as opposed to the resetting case. Here's the resetting case right here. It does not recognize that because resetting, it cannot reuse previous bits. There it is. We have Mealy versus Moore state machines. So we also have resetting versus non-resetting state machines. So that gives us the ability to design 4 different types of problems, 4 different state diagrams. They're all going to be a little bit different. This is that problem. We're looking for this 101 sequence on this thing. We want to do a Mealy and a Moore, and it's resetting. So here we go. The idea for these state diagrams is don't get stuck. It's always a question of where to start. Technically you could start anywhere and still end up with the same state diagram, but we're going to start at sort of the beginning, and the beginning is going to be the state where I'm looking for a 1. So I'm just going to call this S underscore. So in this state I'm looking for a 1. If I don't get a 1 on that clock edge, I have to keep looking, and I'm going to indicate that with an X bar. And if I do get a 1, I can transition somewhere to the next state, and we'll call this S underscore 1, meaning that I found the 1. We'll make this our Moore version, and so what we have to do is indicate that we have not found it, so we put a Z bar in there. Okay, so this is going to be X gets you to the 1, so essentially the X without an overbar under it means I found a 1. So when I find a 1, I get to go to this next state. In this state here, it means I found a 1, and now I am looking for a 0. So there's 2 things that can happen. Okay, so in this state, there's only one input. I've covered both of them. I look at the state. I see 2 arrows exiting this state. This state is happy. It's complete. Now here we go. This state, I have to count for X bar and X. If I get another 1, I don't have to start over because another 1 is still the first bit in the sequence. I can just stay in that state. The issue is if I get a 0, that's what I'm looking for, and I get to go to the next state, and we'll call that S underscore 10, and this is X bar. Here's the 1, and here's the 0. I'm going to check this state out. I have 2 arrows leaving it, one for the X, one for the X bar. That looks good. I better put a Z in there. Okay, Z's a 0. Okay, in this state here, while we're at it, Z is also 0 because I still haven't found 101. In this state, 2 things can happen with the input. I can find a 0 or I can find a 1. If I find a 1, that's what I'm looking for. If I find a 0, such as a 1, 0, 1, 0, 0, I have to start over. 0 is not what I'm looking for. And so we'll say X bar. But if I do find a 1, this is going to be S underscore 101. That is what I'm looking for. I get to turn Z on, and that's good. That means, once again, I found a 1, a 0, and a 1. I'm done with that sequence, and I'm almost done with the state diagram. What I need to do is I have to look at X and X bar from this stage. This is a resetting, so I can't use anything. So that means I can't reuse the old values. So if I can't reuse anything. So what's going to happen here, if X is a 0, it's nothing I'm looking for. If I get a 1, essentially that 1 becomes my first value of the next sequence. So it's 1, 0, 1, 1 sets me here, 0 doesn't get me anything. Here it is, more resetting, and I'm going to look at this and see there's 2 arrows coming from each state because there's 1 input. I'm going to call it done. So that was the more version. Let's do the Mealy version. It's going to be similar. And the output Z bar, and I go to the next state. This is S underscore 1, X, and that means I got a 1, but the output Z is still 0. I haven't found 101. Okay, from this state, I got 2 arrows exiting that state. That's good. So very similar to the other diagram. If I get an X, I stay in that state. Outputs is still 0. Okay, so if I get, let's see, if I get an X bar, that's part of my sequence. It's still not the full sequence, so the output Z is a 0. And I'll come to this state, and this is S underscore 1, 0. Remember, here's 1, here's 0, and looking good. This state has 2 things leaving it. This state have 2 things that could go on here. Either X equals 1 or X equals 0. So if X equals 0, that's 1, 0, 0. That's not what I'm looking for. I go back to the start state. So this is X bar, Z bar. If X equals 1, that is what I'm looking for, because that's 1, 0, 1, but I can't reuse the 1, and so I also go back to the starting state of X and Z. So each case I go back with a different output. These are the 2 versions here. Notice that these bubbles are empty because the output is in fact set next to the input, which is set next to the transitions because it's a Mealy machine. Looking at these 2 diagrams here, you see something that's very typical of state machines, of Mealy versus Moore. The Mealy typically has less states, or whatever, the Moore has more states, and that's one way to remember it. The Moore has more states, so that's one clever way to impress your friends or something. So these are the 2 resetting versions. Let's go on to the non-resetting. In the non-resetting versions, these are going to be very much similar. We'll do more. But we can, once again, we can reuse that 1. So here's S underscore is X bar, X, and Z. Haven't found it yet. Z, S underscore 1. Okay, so in this state, very much similar to the other one. I have a X, and if I find a 0, I get to go to the next state, which is S underscore 1, 0. Here's your X bar. Okay, and so this first state, I have 2 arrows leaving it, X and X bar. Same with this state, 2 arrows leaving it. That's good. So here we go. If in this one, this is my S underscore 101, and I get that when I have an X. Otherwise, if I have a 0, which would be 100, that's my X bar. I go back to the beginning because 00 is not in the sequence. I have to start over. So this state has 2 arrows leaving it, an X and X bar. That looks good. So if I get a 1, 1, 0, 1, and another 1, 1, 1 is not in the sequence, but it is the first value in the next sequence. So I get to go back to this this state here, which means I found a 1. But if, check it out, if I get a 0, I got 1, 0, 1, 0, 1, 0, 1. Okay, because I can reuse previous values, essentially I have a cycle here, and we'll make this correct here to make it right. This is the state that indicates I found it, which is 1, 0, 1. Z turns on. All the other states, output some more output, Z is turned off. So let's do the Mealy. Similar, S underscore. This is S underscore. X bar, Z bar, X, Z bar, looking good. This S underscore 1, this is the state where I found the first 1. So I look at this state, it looks complete because I have 2 arrows exiting it, an X and X bar, that looks good. So I know I'm going to go to another state here eventually, S underscore 1, 0. I go there when X is a 0, Z bar, Z is still a 0, the output, and finish up this state. If I keep getting 1s in this state, I get to stay in that state because 1 is the first bit in the sequence I'm looking for. Okay, so there's 2 states there. They both have 2 arrows exiting it associated with X and X bar. So the question is, if I get another 0, if I'm in this state and I get a 0, which is a 1, 0, 0, that's not going to help me. I need to start over. But the issue is if I get a 1, that becomes 1, 0, 1. That's when the Z turns on. Okay, so it's 1, 0, 1, and the Z turns on. I get to keep going back and forth on these. So once again, you see that the Mealy state diagram has 1 less state. That's what we're looking for. So those are the 2 examples, and there's some ramifications of that we need to look at right now. Here's the associated timing diagram. I noticed in this one I used 0s and 1s instead of X's and X bars. But you can see what we have here in state A, X is a 1. Here state A, X is a 1, causes me to transition to state B. You can see that transition right there. In state B, X is a 0 right there. That causes my transition to state C. In state C, X is a 1, causes my transition to state D, and that's when the Z turns on in state D. This is actually the non-resetting case. And I can see it's non-resetting because it's 1, 0, 1, 0, 1, 0, etc., etc. See something interesting when we compare them. Okay, so this is also non-resetting. Now the interesting thing is, what you can see here, because this is a Mealy diagram, the output can change in the middle of the state, which it does. So here's your 1, here's your 0, and this is your 1 right here. Here's the 1, 1, 0, 1. That causes the output to turn on. The Z turns on because it saw a 1, a 0, and a 1. But check it out, it changes right in the middle of the state right there. And that's a characteristic of a Mealy output. The more outputs could not change in the middle of the state. They could only change on the clock edges. So you can see that in a second here. So the comparison of these 2 is it's very much the same, except you can see that this more machine up here, this is more machine. You can see all the state changes are synchronized with the clock edge, but not the case with the Mealy machine right here. The output can react to the input, and which it does at this point right here. The issue is, in the real life, that's indicative of the fact that output can change faster in a Mealy machine and than it can in a Moore machine. So more on that later. Important thing is to realize that the differences between a Mealy and a Moore machine in the context of timing diagrams. Here's an example problem. What we have is a state diagram, and I've partially filled out timing diagram, and I need to fill out the timing diagram. So the first thing to notice is this input here, which is an asynchronous input. That means when that input is asserted, it makes something happen. It's not synchronized to the clock edge. We represent that with an arrow coming in out of nowhere. It's different than a state-to-state transition that we've been used to. It comes in out of nowhere. That's your asynchronous clear. The issue here is your asynchronous clear, it puts the state machine into state A. There's another thing to notice here is when you're doing these problems, go look for those asynchronous clears and mark them, because if you don't, you'll forget. So what we're going to do here is we can see that at this point it goes back to state A, and so I don't know what the other states are, but we'll figure it out. In state A, what controls the transitions is X. In state A, X is a 1. For state A, X is a 1. It goes to state C. In state C, X is a 1. It stays in state C. Okay, then we get this asynchronous issue right there. In state A, here we are, we're in state A right now. X is a 0. In state A, X is a 0. Here we go, you can't see it much, but it goes to B. In state B, X is a 0, causes it to transition to state C. In state C, X is a 0, causes a transition to state A. In state A, X is a 1. X is a 1. Find it here, X is a 1 right here, and it transitions to state C. X is a 1, blah, blah, blah. Okay, we are done with the states. Now we can go fill these in. So I'm going to do some shortcuts here, something you can do yourself. Z1, it's the more output. It's a matter of state. So I'm going to look for everywhere I'm in state A. If I'm in state A, Z1 is a 0. There's Z1 in state A, state A, state A. Okay, so everywhere else, I'm not in state A. I can see that Z1's a 1, so I can go fill those in. In a structured format here, Z2's the mealy output. So in state A, I think I'm going to go ahead and erase this so I can see it. In state A, you can see, look at these, you can see that the output is the opposite of the X input. So in state A, the output is the opposite of the input. X is a 1 as input, the output's opposite. State A. Output's a 0, state A is opposite. State A, it's the opposite, so this is 0, 1, so this should be 1, 0. That's it, that's all for state A. For state B, if I'm in state B, here's the output for state B. It's a 1 all the time in state B. It's not dependent upon anything else. Once again, here are the two 1 outputs. Here's state B, and I'm done with that. Okay, in state C, what we have is output is the same as the input in state C. Output is the same as the input, so input's a 1. Okay, so it's going to follow it in state C. This is following that. In state C, I got a 1. In state C, it's following the output. So this waveform is going to look like that one, and I'm done on that one. So summarizing here, I filled in all the states because I can do the transitions, and then I filled in the outputs one by one. I was very careful to take note of the asynchronous clear signals at the beginning of it. I made a little marker there so I didn't forget. Okay, so when editing these videos, I found a mistake in here, so I wanted to correct that mistake. The mistake is right at the C point right here. The C should be following X. X is a 0 there, and it should look like that. And there's our repair for this problem. Sorry for the trouble, folks. Okay, so this is our last example problem. This turns out to be a somewhat involved problem. It's truly modular design. It's truly a circuit where we need a state machine to control it because it's doing some interesting stuff. So what we have here is a circuit that has an A and a B on the input, and when they're equal on a rising clock edge, the circuit's going to output FF for 3 consecutive clock cycles, or until a button is pressed, so whatever is shorter. Essentially, if it's not outputting FF, it's outputting A. So let's get the high-level black box diagram first on this one. This is a circuit, and there's really, the inputs are 8 bits, and this is the valve here. We got A coming in, we got a B coming in, these are both 8 bits. Got a button, and we have a clock signal. This is going to be a clock synchronous circuit. We need to handle it accordingly. Next thing we need to do is draw the circuit. So this is modular design. We have to look at the circuit and see what it tells us. Design something when A and B are equal that essentially calls out for a comparator. The output, it's telling me it's either outputting FF or A. So somewhere in there I have a mux. It's outputting one of 2 things. There's the valve right there. I think I'm done with that. I know I for sure need a state machine to control this thing. It's going to be clocked, and we'll figure this out in a second what this is. So this is a mux. It's choosing one of 2 things to output here. It has a control variable. This comparator kicks out a status, and so the very nice thing about this is the status signal is going to be fed into the mux. This is a control signal. This is going to be the output of the state machine because the state machine outputs control signal. Those are our modules. I'm ready to start filling this in with what I know. So one of the things here is it's going to compare A and B. These are 8-bit inputs, and it looks good. Either going to output FF or A. So I can put this like this. Okay, that looks good. And lastly here, I don't really know what these values are, so I can plop down anything, and I think I'm done with this circuit at least. The last thing I need in this is the state diagram, and I think I'll put it up here. And this is I want to try to give it a decent name here. Okay, and I forgot. The button is going to help control this circuit also. Okay, the button has nothing to do with the modules up here. It's going to be essentially a status signal into the state machine. So this first input, I'm just trying to think of a good name for it. A, B, N, E, Q. So A, B not equal. It's going to stay in this state so long as they are not equal. Okay, once they are equal, I have to go somewhere else, because once they are equal, I have to do something different. So this is the case where they are equal. This is a good start, and so what's the issue here is in these states, I have to put a select there. So if they're not equal, it is going to be outputting A. A is connected to this 1 here, so it's just select. But when they become equal, it's going to output the other value, which is FF. So you can see in this state, we will turn the select off. Turn the select off causes it to output FF because FF is connected to the 0 there. So I'm in this state. I have to stay here at least 3 clock cycles or until a button is pressed. So here we go. If there's a button press, I'm back to the normal processing. Otherwise, I am going to go over to this next state. If the button's not pressed, EQ, we'll call this EQ 2, and I'm still in that wait pattern, and I'm still outputting FF. And notice that EQ has nothing to do with the circuit anymore, and I need one more of these guys. I believe this S EQ3. That's the button not pressed. Of course, if someone presses a button in this state, it's going to go back to the start state. And so once again, I have a button and a non-button, a button and a non-button. And this state is the third state. It's going to transition back to the beginning state unconditionally. So this unconditioned here is actually BTN or BTN not, which is the same thing as 1, which essentially means it always transitions. The last thing I need to do for this circuit is state what select's doing. If I'm still there, select is still outputting FF, and I'm going to call this problem done. Notice that I did not connect the control and status signals. If I connected these up, it would get really messy. I have AB button and clock. I didn't put a clock here. It's understood to be there, but I do have an AB and button. The output's val. Output is listed. Everything matches. I've got all the bus indicators all set in there, and then I'm going to call this problem done. This was the engineering step. This is the hardest part. This is the way I essentially generate delays using a state machine. I had to state in outputting FF for 3 states at the very least case, or look for a button press. This is the way to do it. So once again, if the button is never pressed, it holds that value 3 states. You can see 1, 2, and then it's going to go here either way. If the button is pressed, it goes back to the beginning right away.